Hi, welcome to this presentation. I'm with someone from Hong Kong, Peru. In this presentation, we are going to present our work on 3D lidar-SLAM in urban chaos. So actually, the SLAM, simultaneous localization and mapping, is an efficient solution for positioning in denied scenarios like the urban. However, first problem is like the vertical field of view of lidar is very small. The second one is a lot of dynamic objects in urban scenarios. So as a result, the drift in the z directions in the altitude directions can be significant. So in short, this is mainly due to two reasons: the small field of view of the vertical directions. Okay, this is the first problem. Second one is the dense dynamic object. Okay, in urban scenarios. So the first one, they propose to use the ground features to relatively constrain the vertical direction, the state estimation in the vertical direction. The second one is tries to integrate more sensors like the IMU to decrease the drift rate in the vertical direction. The last one is almost the latest one. They integrate even more sensors like a camera to mitigate the drift in the vertical direction. However, they try to decrease the drift rate. They cannot essentially solve the problem. So all I did like this. Okay, let's see the urban scenarios of like Hong Kong. So we can easily get for almost all urban scenarios, we can detect the feature points from the ground. It means it's possible we can detect the ground planes. So our assumption is that if the height of the road is almost unchanged in the tested trajectory, so we can get two constraints. The first one is the z-axis, the direction of the vehicle system. The z-axis of the vehicle system is almost vertical to the ground plane. So the second one is the distance from the lidar center to the ground plane is almost unchanged. So based on the true assumption, we can get one more constraint. So this is loop closure from lidar-SLAM. This is the feature detection association from typical lidar-SLAM. So by adding the ground plane constraint, we get a new solution. Okay. So this is the vector graph by integrating the state, the ground plane, and the loop closure and the lidar odometry. So by doing this, it has three key features. Okay, the feature is based on long. The ground plane is detected using a RISC, and loop closure is detected using an NDT. Okay, let's see the sensor setup, the scenario, trajectory, and by using the proposed method, the drift using the conventional method is about 30 meters, can be decreased about 0.2. And in here is the quantitative result. For example, the active direction is about 40 meters, can be decreased to like 0.4 to 0.4. Okay, using the proposed method together with the closure. The second experiment is like this. It's slightly more complicated. Like the ramp road over here, but still our method can significantly decrease the drift in the vertical direction. In here is the ground truth, and the blue one is the proposed method. So in here, we can decrease the overall altitude error from 7 meters to about 0.2. Okay, let's see the references, and feel free to contact us, Dr. Su, and here's our lab. Okay, thank you.